All right. I think that we can start. At least there are 20 of us. So today we will have the second session in artificial intelligence, and we will talk in details about large language models, and also we will have a broad perspective of neural networks and how they evolved. So how we came to architecture of state-of-the-art large language models. And today, this presentation will be made by George, and same as I was talking the previous session, this presenter is much more experienced in all these technologies than I am. So floor is yours, and let's have a interesting and a very helpful presentation. Okay.
Hello, as Timur said, my name is George. I'm a lecturer and professor in Moscow State University and in Central University. That's new university that was made by T-Bank, that is very popular in Russia. So today I would like to talk about how we moved from simple linear regression to tremendous large language models. So we'll start with core concepts in machine learning and not very, but gradually move into advanced architectures like transformers. So let's start from defining what is natural language processing. It is a subfield of computer science that focuses on enabling machines to understand and generate human languages. It covers tasks like uh, translation, sentiment analysis, relationship extractions, uh, different classifications, question answering, and and many others. Um, so NLP uh, works with human language. What is language? Language is morphemes, words, syntaxes, semantics, sounds if we work with advanced language models that can preprocess sounds. But in general, we can describe this task as predicting the next word in context of another word. So we are predicting the probability of the word T can be generated, can happen in context of all previous words. For example, if we have text London is a capital of Great Britain or is a capital of, the most probable next words will be Great Britain. Machine learning can be separated into three main categories that are supervised learning when we have correct answers for data set, unsupervised learning when we don't have correct answers, and reinforcement learning. In my mind, it will be more correctly to say that reinforcement learning is a combination of supervised and unsupervised learning, but it could be described like this also. So we'll talk mostly about classification when we have to assign categories to our data. And every NLP task is classification, as we'll see in the future slides. But let's start with some familiar concepts like linear regression. For example, we have tasks to predict inflation based on different parameters. For example, they are GDP, unemployment, and interest rate. So we just make a weighted sum of these parameters. So our weights are B0, B1, B2, B3. And this is our result. We can use any activation function if we want to deform our result, like in logistic regression. We use sigmoid function that deforms our result into field of 0 to 1 from field of continuous values. And linear regression and logistic regressions are actually neural networks, but very simple. Let's have a look. Let's have a look on a feed-forward neural network that was used for like every task and in nearest past, like in nearest 20 years. That's actually a combination of linear regressions. For example, we have uh, uh, four parameters that going inside our model. So, for example, it will be the same as for linear regression, constant, GDP, unemployment, and interest rate. So, if we only have one dot on the next layer, for example, this dot, it will be the linear regression. So we will have the weighted linear combination and only one output. But if we add more outputs, more weights, we can produce multiple outputs. So we'll have a combination of linear regressions. If we were add some nonlinear functions that are called activation functions, sigmoid is also in nonlinear activation functions, but it's a function, but it is not widely used today due to some problems. We can make our neural network nonlinear, so it will learn nonlinear features of our data. And if we stack multiple linear layers with nonlinear activation functions, we'll learn a lot of nonlinear interactions in our data. So text is just a set of words and letters, but computer doesn't work with text. It works with floats, integers, and other decimals. So we have to preprocess our text into some decimal format. These formats are called embeddings. So we represent our text, our word, or our letter in a form of floating point vectors. As usual, they are highly dimensional because words contain a lot of meanings. So we use like 100 floating points vectors for every word, for every token. So let's talk about what is a token. Firstly, we need to decide what part of text we'll encode later. So we have to divide our text into parts, into tokens somehow. For example, we can divide our texts into words. I am trying to learn binary, so we can divide into words. But we can divide it in subwords. For example, uh, trying can divide in try, why, ink, and etc. We can divide it by phrases. We can uh, divide it like we can extract service tokens and quotations from it. We can extract numbers and much more else. Uh, but that approach will lead to not very great results in terms of dimension of in terms of amount of our tokens. We'll have a lot of tokens that we can't preprocess. So in 90s and early and at the beginning of the century, uh, the main approach was to remove all unnecessary information from our text. For example, remove mutation, convert everything to lowercase, remove different stop words like to, but, all, to, me, that has low or unnecessary information. Apply lemmatization, like trying, convert to try. Uh, and the result will be try learn binary from that large text. So we'll lose a lot of information, but at least we can preprocess this sentence. But today this method is not widely used because, as we have seen, it will it probably will drop a lot of information, too much of information. So, a more advanced approach is byte pair encoding. The name comes from information theory, which is why it contains byte. It was originally used for data compression. So let's see how it works. Firstly, I will describe the algorithm, and then we will see step by step how it works. So firstly we should define the base vocabulary. Usually, it's just unique characters characters in the text. Until the required vocabulary size is reached, we should repeat several steps. So these steps are we go through the entire collection of text and count each pair of adjacent tokens from the vocabulary. Then we select the most frequent pair and add it to vocabulary. So let's see a simple example. For example, we have a table of text, our data set. So there are 10 texts hug, 5 texts pug, and etc. So how will the base vocabulary look like? As I have said, it will it will consist of unique characters. So we have 7 unique characters. They are B, G, H, N, P, S, U. Uh, sure. Okay. Uh, okay. That's a comment of our another lecture. So that's very interesting. You can read it while I'm talking. Um, so we are counting each pair of adjacent tokens from our vocabulary. So the adjacent tokens from our texts were like HU, UG, PU, UG, and etc. So the most frequent pair is UG. We choose this pair and add it to our vocabulary. So we add it. Uh, so afterwards, we do the same. And until the size of vocabulary is reached. However, this approach isn't the best. The best one is byte level, byte pair encoding. This approach actually uses bytes because the computers see letters as bytes. So why not encode bytes instead of letters? This helps to solve several problems. For example, there are more than 100,000, 155,000 characters in a computer. However, there is only 256 unique bytes, so we have very small base vocabulary. And we never will have an out of vocabulary problem. For example, our user will send, we have an English model, and user will send us something in Chinese, and this won't cause any problem. We'll process this somehow, not very perfectly, but it will be processed somehow. Um, so we defined how we can get tokens, small pieces of text that will be somehow encoded later. Now we'll talk about how we'll encode these tokens, these pieces of text. The most the simplest way is to use statistical embeddings. So just count word accuracies in our text. We create matrix that has shapes of number of texts and unique tokens. So we have in this small set of text, we have like 11 tokens. And then we just count how often, how much times each token occurs in our text. So this puppy is one, A1, puppy one, and this one. In text, this dog and this puppy is we can see there is two times, so there is equals two. This approach is also called bag of words because it doesn't take account the order of our text. So it's the main problem of our text of this method. So it doesn't work very well, and it is very rarely used nowadays. The other problem is that it is very high dimensional method because we have matrix of size equals to unique tokens in our data set that could be thousands, millions, and even more. Moreover, the results of vector space is very hard to interpretate. Okay, you got it. Because it doesn't catch semantic meanings. But there is methods that can catch this semantic method. They're called trainable embeddings. And the main idea of trainable embeddings is that we learn the embedding from the context of our text. For example, uh, we can say that there is word cheese by the context of our phrases. For example, cheese is loved by mice in cartoons. With wine, a cheese plate is often served, and etc. So we don't see word cheese on the slide. However, we know that this empty space should be filled in by cheese with cheese. So that's the main idea of approach that is called word to vec. So word to vector. We have a sliding window that like slides of our text. There is a central word and context around this word, and we want that vectors embeddings of central and context words were similar, were close together in meanings, because we know that similar words could be seen in similar contexts. So how it works? We want to predict we want to predict uh, the probability of every context word if we know the central word. And theta is are parameters of our trainable vectors. So we have a lookup table where, for example, for word cheese, we have one vector. For word cat, we have another vector. So when we see word in our text, we just pick the exact vector from our lookup table from our dictionary. The probability could be calculated with softmax function. So here how it looks is just a dot product of two vectors, vector from context and vector from center. And in the lower part of our fraction, we have a exponential sum of all context vectors to all vectors from our vocabulary. This is a very computationally difficult operation. However, there are a lot of smart approximations that lower these computation difficulties.
So what is this small w actually means?
Uh, Small, they're all small.
Yeah, this one. So this is the conditional probability of what exactly?
Probability that we see vector from context conditioned by that we know that the central word is like the one we see.
So we want to predict a conditional probability of a next coming words, or what's the meaning of it?
Not next. We just want to learn embeddings that are close in meaning. Now we don't predict anything. We're just minimizing the probability function so that all the embeddings that are the embeddings of close words will be close mathematically too.
So capital V on the right-hand side, this is the entire vocabulary, and we take a small w from this entire vocabulary. So what do we take from this entire vocabulary?
Uh,
A word. Is it
you
a
mean
word?
a vector? We take all the words, then we pick a vector from the lookup table.
Okay, I see. So small w actually means a word, and I mean
Here it means yeah a word, and here it is a word too, but here it means the vector representation. So it's a word everywhere. Yeah,
okay, I see.
vectors are those.
And are these embeddings here again like a sequences of zeros and ones, or now there can be any number there?
They can be any number there. The size of embedding is so-called hyperparameter. So we set these before training. It can be any size. So like 100, 200, any size.
Hmm. I see. So the main intuition behind this approach is to get embeddings that would represent what? How words are related to each other in the sense that how close they are appearing together. This is the intuition.
Yes, exactly,
So it's
exactly.
not about semantic relevance, semantic how they close in terms of semantic sense, how we understand their kind of closeness. This is the way just to define how often they appear together, close to each other.
Not like often, but if they appear often, I mean, if they appear often, they should have closer semantics because our probability function will make them similar. So we want to maximize this softmax function, and it will reach its maximum one when these vectors are completely similar. So the dot product will be maximized. And this will happen only for semantically close vectors and semantically close words.
Mhm. So we hope that this approach will try to catch semantic similarity uh, in some sense.
Yes, in large text data sets, it should catch, and as the experiments showed, it's worked very well.
I see. Very good.
So, learning these embeddings will get us will get us very interpretable embeddings. For example, there's a very popular example when we have like equation where king minus man plus woman equals queen. So if the training is done correctly, uh, this mathematics works on any word in our world, in our training domain. Uh, okay, so uh, okay, narrow embeddings are the same. The idea of narrow embeddings is the same, but they train a bit different because there is more parameters in neural network. So they train with the parameters of neural network, but the main idea is the same, still the same. Uh, so let's now pass to large language models. Uh, so large language model is works as any other model in machine learning, deep learning, and everywhere else. It just predicts something. It isn't intelligence. It isn't AI. So as I said, uh, it will predict the next word, or it can predict is a sentence positive or negative, or does the article belongs to economics or medicine, and much more other. It can solve much more other tasks. As I have said, every language problem is classification. So let's start with a very simple classification task, which is called word classification. And example of this task is part of speech tagging. So when we want to define which word belongs to which part of speech. It can be solved with recurrent neural network. This is an compared to feed-forward network, it's an advanced block, but it's not much more difficult. The main idea of recurrent neural network is that it saves information into hidden cell inside it. Uh, so it goes through our sequence step by step, word by word, and accumulates information is inside itself. So for part of speech tagging, we can use recurrent neural network. So we have word, it goes through our recurrent neural network, and we predict its part of speech. Then some of information is accumulated into recurrent neural network cell, like in its head, in its mind, and then we pass to another word. We apply same weights, same parameters, nothing has changed to our next input. Then we predict the next part of speech. So the inference is finished as the sequence finishes. But today we are talking about large language models, and they don't work like part of speech tagging models. They work a bit more difficult. So in general, they solve a sequence to sequence task. So we have one sequence, and we want to transform it to another sequence. The best example of sequence to sequence task is machine learning translation. So why using such simple architecture for machine learning translation that we used for post tagging, why it will perform poorly? Any ideas? Is anyone listening?
Yes, at least I am listening. So could you perhaps a bit expand your question?
We have probably someone wrote something in the chat. Okay. I can just answer if no idea. So or I can repeat the question or what you want, Timur.
No, just put some hint perhaps inside, so it will be easier
Uh,
to
Most of the
read.
languages, for example, we're translating from English to Russian, and English has traditional English has the other order of words comparing to Russian language. So and moreover, we have different grammatics, semantics, and other. So why the solution that was used for part of speech tagging will perform badly for machine learning translation? So why we can't just translate word by word?
Maybe because some similar sounding words have different contexts in other languages.
Yeah, that's a problem, but that's not the problem of the architecture. That's just a problem in general that it could be solved only by adding more data to our data set. Uh,
I think we have an answer in the chat.
uh, yeah, see, that's looks the same as the our fellow listener said. So the main problem is that when we translate, as I said, the main languages have different word orders. So if we translate word by word, uh, in most of the cases, we'll get incorrect translation in terms of grammatics because word orders differs from language to language. Yeah. So Alex mentioned right things in the chat. So we need to use another architecture. We need to process the entire input sequence, so accumulate information about our text in a hidden cell of RNN, and then only start generate our output. This worked great, but only for short sequences. For long sequences, it performs still poorly. Why this can happen? Here it is.
Perhaps we can elaborate a little bit and say that the main idea here is that we process the entire sequence and put this information into basically one vector. So
Yeah, hidden
like a
cell
memory.
is just one vector. It can be small, it can be large, so we can choose any size of this vector. But
So and that's a problem, right, everyone?
We
yeah,
have
Problem.
one message in the chat. There are more words to forecast guess. I'll explore.
This can be a problem that the size of input and output sequence will differ because the languages are different and they have different grammatics like articles and some words couldn't be translated into only one word. For example, only two or three or more words to translate something from one language. But the main problem is in that cell in RNN memory that it's a fixed size vector. And it updates every time we get a new input. So we have looked at first input, updated our vector, second input, updated our vector. We looked at input number 1000 and we updated our vector, but we have that a vector of a fixed size and we can't encode all information about all our sequence in this vector. So model, our RNN, will forget information about first inputs when it will reach the last inputs. So the translation will be poor. So how this can be solved? In 2014, Andrei Karpathy released a paper where he showed the world his ideas about attention mechanism that was used for machine learning translation in Google. So the main idea of attention is that we save all the vectors from our encoder or from our first part of model. So our model divides into encoder and decoder. Firstly, we encode our sequence and then we decode it. So now we'll save all the information from our encoder. So how we do it? Just use our RNN. We preprocess the first token, and then we will get a vector, it's some preprocessed vector, and we'll save it. Then we are doing the same thing with our tokens and save all the information for the future decoder step. So we saved everything. Then the decoder. Okay. Michael wrote some interesting notes in the chat. If you want, you can read. So the decoder starts working. Firstly, it generates a service token that's called beginning of sequence. So we let the decoder know that we have started our generation. And it generates the first vector representation. Then we have to predict the first token of our translated sequence. How we do it? So the attention mechanism kicks in. We can compare, like we are making a dot product of our last vector from decoder with every vector from encoder. So if I'm making dot product, we get a scalar value. We get a scalar value for every operation. So if vectors are similar, if meanings in these vectors are similar, these dot products will be maximized. So that means that with this operation, we can find the most useful information from our encoder that we need to use right now for decoder step. So then we use softmax function to transform our distribution to 0 to to transform it to 0 from 0 to 1, and then we'll get weights for every value. So we have some weights from 0 to 1 that together sum up to 1. With each weight, we multiply each weight with every vector from encoder, and then sum everything up to get one vector with aggregated information about encoder. Then we just pass it to decoder and then solve the classification to predict the next word.
Okay, but where does decoder take these words from another language from? So encoder performs with I saw a black, right? So this part works with initial language. The second part, the decoder wants to produce a sentence translated to French, as far as I understand. So it's not pretty clear how decoder makes this transition from one language to another language. So decoder needs to predict the next word in another language. So where decoder picks and how he understands the probability distribution over these French words.
To start with, we have a paired data set with a translation from one language to another. Then we make tokenization for every language. So we have tokens for English and for French. Then we doing this all operation, and as I've said, all NLP tasks work with classification, only classification. So the prediction of next word is that also a classification task, but it just has a lot of classes. The dimension of prediction equals to vocabulary of our French language. So we have 10,000 French tokens, or even more, 100,000 French tokens. So we'll solve a classification task to 100,000 tokens. It's a very large output. However, if you have a lot of data, it works well.
Mm-hmm. So this mechanism of attention here, like, why do we need this? So why, and what it does exactly? So it understands the specifically what, how words are connected in different parts of a sentence, or what this attention does.
It helps decoder to get more information about initial sequence that was preprocessed by encoder. So it let the decoder look into information like in the past information that was given to it, and then finds the most useful information out there.
Mm-hmm. So it's a mechanism that tries to understand what do I really need to get from a previous context in order to predict the next word.
Exactly.
So it's like a process of asking myself and answering, like, what do I need in order to do what, in order to say what. And yeah, okay, seems a bit more clear now. Okay.
That worked well. However, recurrent neural networks have several problems, and one of them that they're kind of complex in terms of computation. So as you can see, the recurrent neural networks have computation difficulty equals n d squared. N is sequence length, and d is the representation dimension. So it's the size of our vectors of our embeddings. So researchers created a transformer, and that was based on idea of self-attention. That computation complexity is lower if we're talking about the representation dimension size. However, it has larger computation difficulty if we're talking about sequence length. However, it can be it's very easy to parallelize transformer and self-attention. So in modern days, for modern GPUs, it's not a problem because they parallelize operations very well. Moreover, its self-attention is better, and transformers are better for learning interactions between words that are very far away from each other. As we know, language is a very difficult structure. Like the first word of a long paragraph could be related to its last word. However, the recurrent neural network works from left to right or from right to left, and it's very difficult for that architecture to catch information. It will be great if we will have a block, an instrument that looks at the whole sequence at one time. So that's what the transformer exactly does. It can look at every sequence. It's at a sequence and preprocess all the tokens at a time. So we will so every token will look at each other tokens and gather information. Okay. So transformer is actually the same thing as we discussed with RNNs when we have attention. But encoder and decoder are a bit different. We have a self-attention, both in encoder and decoder. And now let's discuss how transformer and self-attention look. So there on the right of the screen, you can see an architecture of transformer that was proposed in 2017. Paper called "Attention is All What You Need." So as you can see, it's the same decoder architecture, but the devil is in details, and the main idea is in that orange small block that is called multi-head attention. That's exactly what is called a self-attention. So actually, self-attention is the same thing as attention between encoder and decoder, but it is performed inside encoder and or decoder, not among them. So somehow we need to preprocess our embeddings into different fields. So they could be different. So these embeddings could have different semantics, and that's how it performed. So for every token, for every embedding in our input, we have 3 copies: query, key, and value. So how can we transform our embedding to this form? We just multiply our data, our embedding X, on matrix W, Q, WK, WQ, WK, and WV. These are trainable matrices. So these are matrices of weights, and they are optimized during training process. So we have transformed our data into 3 different instances. Then, as we did in attention and in simple attention between encoder and decoder, we calculated attention scores between vectors from encoder and decoder. So here we do exactly the same, and we compute attention scores between our query matrix and our key matrix. Then we have to transform this result to okay. So let's pretend that a vector wants to know who he is in this cruel world. So he asks a question. Who am I? So we need, firstly, to ask this question. We need to preprocess this vector to query form. So question is a query, so we preprocess to query form. All the answers this vector can get only from keys. It will look on every vector in the same sequence. So the vector wants to understand who surrounds him. That's why he asks these questions. He asks every vector around him in the sequence. So we need to get the key vectors. So how we get it? We just multiply every input vector on weighted key matrix. Is it clear?
I would say that the way how to understand what it actually is can be metaphorical in some sense. So this approach with questions and answers, it's a metaphor. So a quick answer to this question, what is it? Is just a matrix. So these are just some parameters, basically, that are involved somehow in all this processing. But this is like a metaphorical analogy. What would be the kind of reasonable sense of these matrices?
You can have another interpretation, actually. You can look at step 2 and see that E is actually a bunch of dot products, right? So we have a matrix multiplication. And when we do matrix multiplication, we do tons of dot products. And dot products are responsible for computing similarities between vectors. So E equals Q times K transpose and stuff. It actually computes tons of similarity scores between vectors stored in Q and K. So we can treat E, which is like the attention score, as a dot product. So this measures similarities between keys and queries. Now, keys and queries are based on X, which is basically our standard embeddings, multiplied by some random matrices that we don't really care about. But if you expand this E equals Q times K transpose, if you put the definition of Q and K into the matrix, into the equation, you will see that the entire equation looks like X times some matrix times X transposed. So basically, you can write it out on paper. So basically, you'll see that E is a massive dot product that looks like X times X transposed. You can basically recall this from linear regression. It also has a similar kind of equation there. So we compute a bunch of dot products using some weird matrix in between, a matrix consisting of WQ and WK. So essentially, this attention score represents a dot product which measures similarities between queries and keys. Now, queries and keys are exactly as Timur said, they don't really mean much. You can try to embed some kind of nice wording into them, but really they are just a bunch of parameters that are that somehow, for some reason, help us build better models.
Actually, they mean something. There are lots of articles that trying to explain how transformers think, and they use they dig into these matrices. So and some meaningful instances could be found there.
Yep. That's the magic, actual magic of machine learning, is that you can learn completely starting from random noise, random parameters. You can apply data into this and learning algorithms, obtain learned parameters, these matrices, weights and biases and stuff, queries and keys, and discover through complicated mechanisms, discover that indeed the learned parameters mean stuff. So you started with noise, didn't actually mean to impose any meaning into them. But now, as a result, you get something kind of interpretable. And indeed, there's a whole field of research that deals with interpreting, making sense of transformers and their parameters.
Yeah, so I think it's always interesting what is inside the black box. So for me, at least as of now, I would say that for me, large language models are black boxes for me. So if it is possible somehow to understand what are these meanings and the interpretation of all these bunch of parameters, it would be very interesting to see how actually it works inside. All right, so I think that we can move next.
So let's see in a simplified way these equations. For example, we have our input X that consists of 3 words, and each word is encoded with 6 digits. So now we have one head. We'll explain later. I will explain later what it means, but now it's one. So we preprocess our data, our X, into 3 different instances, into query, key, and value form. So we just multiply like matrices, our data on weighted matrices. So we have new preprocessed form of our data. Then between Q and K, we calculate dot products for every row, and we'll get matrices of weights. How much should, for example, the first word attend to the second word. Then we have a weighted matrix. We multiply it with V, with our values matrix, and then we get output, our final result. So it's just matrix multiplication. What else we have in transformer? It is residual connection. So we just add input to the result of our self-attention that helps to train deeper and better models. Then we also normalize our data, so it will have 0 mean and 1 standard deviation. And it also help train larger and deeper models. Then we have a feed forward block. That's the same block from the beginning, where we have multiple linear regressions running in parallel. And then we're doing add and norm again. What is head in multi-head self-attention? We can divide our data vector into parts. So, for example, the three first digits digits of our vector describe like punctuation of our text. The 3 last digits of our vector describe like words of our text. So each part of our vector learns something from our text, and we want it to learn something different, some different aspects of our text. So we divide vector into parts, and for every part we have different weighted matrices Q, K, and V. So we have a bunch of smaller matrices that are computed separately. We have different attention scores for every small matrix, and different value matrices. And then we just concatenate our result back to keep the shapes as they were before transformation. That's the head. So that we described the encoder. However, we also have a decoder part. Actually, it works completely, almost completely the same. There are some differences. For example, the first difference is masked multi-head attention. So we just add mask to input of our self-attention block. So the decoder will attend only tokens that it has already generated when learning. And we also have cross attention. That's the same as attention between encoder and decoder in our RNN architecture. So we have K and V from encoder and Q from decoder. So decoder asks what I need from encoder. It gets it from, and it gets information from K and V that are from encoder. And add and norm are the same. then we have a linear layer and a softmax to get output probabilities to predict the next sequence, or the next token of our sequence. So now I guess we have not a very clear, but have a concept of how LLM works. Now let's talk about how can we adapt it to our tasks. So the most simple, the simplest way to make LLM work as we want it is to write a prompt, a short instruction that asks our model to do something without updating its parameters. It should contain some instructions, context, examples, like role, for example. Explain me something like a PhD student, or give me a reply in format of PDF or etc. So prompts can be zero shot. So we don't give any examples to our model. We just write our simple short user prompt. However, it doesn't work great for smaller models. We can show models some examples. So it will be called, if we show one example, it will be called one-shot prompting. If we give more examples, it will be few-shot prompting. As example, we can give model a task to write, I don't know, a small test for machine learning course. We want exactly 5 answers for every question, and sometimes model doesn't know what means 5, like it doesn't have an embedding for number, so we can just show it an example, right? And one question that consists like A, B, C, D, E answers. So it will be 5, and it will probably create fine answers. Probably not. No one knows. But what if we created great prompt, in our opinion, great prompt, but our model still doesn't work as we expected? As I've said, every word, every token relates to a vector that we get from a lookup table, and only afterwards this vector is passed to model. So why not directly learn vectors that represent the correct prompt? So that's the idea of fine tuning of or soft prompt. So we are learning the correct prompt, correct vector representations that will be suitable for our task. The main problem is that we need a data set with correct answers to fine tune our model. How soft prompt is performed? We don't need to move all the weights of our model, and in most cases it's even not possible because we don't have so much computational resources. Large language models are large, like you need a very expensive GPU if you want to train all the weights of the model. So we just add two, three, or probably more, but not much more trainable vectors to our input, like H vectors, and train it on a downstream task, on our specific task. There is another fine-tuning method called LoRa that stands for low rank approximation. So it performs better than soft prompt, but could be done only if we have more data than data for soft prompt. How it's performed? We change all the way, or not change, we add low rank adapters, that's the linear layers that on every weight matrix of original model. So we had weight matrices that transform our input to query key and value. So we add their low rank adapters that have less parameters that original weights, and then we train these weights on a downstream task. It also can be done on low resources. However, you need a bit more resources to do that type of training, but not much more.
And a bit of forward-looking as usual. So fine-tuning will be a part of your take-home assignment. So yeah, and it will be an interesting task. I think that it will be kind of a fun, of course, but you will see everything soon. Kind of.
It's not hard. There are lots of libraries that perform this fine-tuning by importing like 2 or 3 classes, and everything works fine. I think the main difficulty is to get all the data from the internet that you need. So
Perhaps we can elaborate a bit more on the goal of fine-tuning. So what will be the output of this procedure? So why we would do this?
for example, we want to style our model somehow. For example, we want model to speak like Trump, like Donald Trump. So we gather Trump speeches and train model on them. So on every input, it will answer as it was like Donald Trump.
So my way of understanding what fine-tuning does is not only a style, but sometimes
No,
it's
not
even
for example,
I
style. Yeah,
agree with
it can
I
be.
agree absolutely with this type of understanding that it is a style, but sometimes I think it's a bit deeper. So the way how you say things is also a representation of your mindset. So actually, yeah, we can think that this model will fake in some sense, or will appear close to a person or close to a task that we give as a training data set for fine tuning. But I think that at least I want to think that way, that this model also learns how to think in order to perform these tasks, whether these are Trump speeches or whether these are specific questions and answers in a specific domain. So for example, you can train your model to answer like an economist, and you can prepare a training data set that would look like similar to examination questions. The similar thing that we do at universities when we have a list of questions and list of answers, and we just try to learn how to answer them properly. The question is what we are doing. Are we just learning it by heart, or we are getting some specific mindset? I want to believe that the second one, although I can be wrong.
So yeah, in general, fine-tuning is just a way to use a pre-trained model to fit better to your task, to your specific task. But there are some special methods for LLMs because they're too large, so you can't just fine-tune all the model. So that's why there are LoRa and soft prompt.
I think that some things also should be said about how many examples you need to have in order to shift these weights. Because so as far as I understand what fine-tuning is, we want to shift, so we want to tilt these initial parameters of a pre-trained model that would be calibrated specifically for these new tasks that we are giving to this model as a process of fine-tuning. And the question is how many tasks you need to provide in order to shift those parameters, because it is a super large model, right? So there are billions or even trillions of parameters. And I mean, can it be done with just a few examples, or we need more?
It depends on model. For example, as I heard, to learn a good soft prompt, you need like 10,000 examples. To learn good LoRa, you need like 100,000 examples. But there are some models for photo or video detection where you need to spot and draw a bounding box for an object. You can fine-tune it like with 50 examples and it will work great. So it depends on model and
Yeah,
task.
absolutely agree. So even it also uh, it also aligns with our experience, because we try to fine tune OpenAI models, and also we try to fine tune Google's models, Gemini. And what George said is absolutely true. So depending on a model, number of tasks that you need to give, implementing fine tuning really can be different. So sometimes even thousands of examples are not enough in order to shift or somehow change OpenAI model. From our perspective, they were the most stubborn, the most stubborn models compared to Gemini, for example.
Okay, so now let's talk about some optimization techniques. So one of them is weight pruning. The main idea of it is just removing some unnecessary weights from our model, so it will consume less RAM, VRAM, like memory, and will compute faster because we have lower parameters. So the main goal of this task is to find small weights that almost or equals 0. So we can just then remove them because they are doing nothing. However, there are a lot other more modern and different techniques that are popular among researchers. The other approach is quantization. So every weight of our model is encoded with bytes and bits. So there are different weight representation, weight formats. And the most popular formats, like 5 years ago, was floating point 32. That means that we use 32 bits for every floating point number, for every floating point weight. That means that we have, but this representation isn't very good for neural networks because it consumes a lot of memory and computation. So scientists created some other formats, for example, floating point 16, floating point 8, integer. So all the weights are encoded with integers like integer 8, integer 4, and some other formats like floating point 6. And the main idea of these formats that we encode weights to a simpler format. For example, these two original weights that differ not too much, they can be encoded only with one quantized value, one quantized weight. So by encoding like that, we'll lose information, but it's okay. We won't lose too much. However, our model will work faster. It will consume less memory, so we can just make our model bigger, and it will perform better with the same computation costs. So for free, with quantization techniques, you can fine-tune, for free in Google Colab, in GPU, in Google Colab, you can fine-tune model up to 13 or 12 billion parameters. And the last optimization technique is model distillation. The main idea is that we have a large teacher model that is great. However, it's too big. We want some smaller model that works great on a smartphone and is relatively small. So we just learn our student model from answers of a teacher model. Not learning it. We don't learn student model on our task directly. We just want to mimic the answers of a teacher model. So as a result, it helps to create small models with performance of bigger models. And it works even better if we compare it to the case if we trained our student model just on a task. So I guess it's all for now.
Yeah, perhaps we can talk a bit more on in the remaining of time about the quantization, because this is what we discussed yesterday with George, and it actually I found a genius two things here. So first thing that I found genius is that how actually our machines, how computers operate with numbers, and what is a number for a machine. And the second thing is why such a method of quantization allows us to implement, to run this model using less hardware. So I think that these two things we need to understand. And perhaps we can also ask it as a question to our audience. So do you understand why this approach of reduction of amount of bits that are involved eventually decreases amount of hardware that you need in order to run this model that will be quantized. Is it understandable or not?
Yes, it needs fewer computational resources.
Yeah, this is what I liked. So and why exactly? So why you need less computational resources? It's super correct, but why?
There isn't as much like the numbers are less are smaller but still comparable.
They are requiring less memory in some sense, right?
Yeah,
So you
like
you
yeah, it's
yeah, the very simple analogy. Think of a parameter that will have like 20 digits after a point. And now think how many resources you will need in order to multiply this parameter by, say, 2. So how many computations you will need to process in your head in order to multiply this number. And say that now you will just round up this number by one digit point. So you will make it smaller in some sense. So you will make it less accurate. But in terms of how you operate this object, it will be much simpler. So the similar thing applies here as well. So the parameters are becoming less accurate, but amount of computational power that you need to operate with these numbers is significantly less. Yeah, this is what I found genius. So you do not change the structure of the model at all. So you preserve the same amount of parameters involved. But what you do, you operate with the accuracy of these parameters. And sometimes you can lower this accuracy, not that much, so not to lose a lot in terms of accuracy of final outputs. But you will reduce amount of computational power significantly. And henceforth, you can use this model perhaps in a smaller devices that eventually do not need this amount of processors inside. Okay, and the second thing that I found where we had a discussion is about this teacher and student model. So what is also called as distillation. Perhaps now we can also discuss together with Michael. Michael is present here. The way how I interpreted this type of training is that, well, in some sense, it looks similar to fine-tuning because what you do, you use output from the large model that we call a teacher model. And we use these outputs in order to train smaller ones. So as we do, what we do when we implement fine-tuning, we have some tasks that are produced somehow. And after that, we use this task in order to train the model to shift the parameters of the model. Here, we want to shift parameters of this smaller student model. But what we use in order to do that? Prepare tasks. So in some sense, we are fine-tuning this student model using what? Using a training set prepared by teacher model. Perhaps so we had a discussion with George yesterday, and we ended it like if you want to understand it that way, you can. But I want to hear also your opinion. What do you think about this interpretation?
I don't get it really, because like if you have knowledge distillation, if you want to train a student model, then you can do this in many ways. In particular, you can have the teacher model generate a ton of text because the LLMs are generative models, so you can have them generate text, and you can use this text as a kind of source for training a student model. So this is really basic. You can use the other models like this. You can have some complicated model of like the entire universe or something, and make a simulation from the model, feed it into a smaller model, and have the smaller model figure out some kind of some ideas in a more simple way. So this is one way of building this knowledge distillation stuff. You can also, I think there's a thing where you can literally attach a kind of a piece of a model to the teacher model, but this is more close to fine-tuning. So I'm not really sure what the understanding is, what the question is, what the discussion is.
Okay. Okay, nice. So
But
anyone
also we can talk a little bit more about this quantization stuff. If you could open the graph, the image, the very cool image from Haber. There is this thing. They show the number of bits, not this one, but from Haber. The one with the bits. In case I'm not sure what kind of audience we have here, but in case this sounds novel or like cool and stuff, it's not novel, not cool. It's a very basic thing because in computers we routinely have two kinds of floating point numbers. So by the way, this kind of number is called floating point number in computers. This is to be distinguished from integer numbers. Integers are whole numbers, and floating point numbers are trying to approximate real numbers. So in computing, we have float 32 and float 64. So float 32 is a kind of number structured basically like this, which holds 32 bits of information, 32 bits. And float 64 holds 64 bits of information. So basically like here, like FP16, but holding 32 or 64 bits. So this is routinely used in computers. Your CPU, your central processing unit, supports these two kinds of floating point numbers. Probably it also supports float 48, but doesn't really matter here. So the main idea here is that it has long been known that you can get various levels of accuracy from floating point numbers by using more or less bits for its representation. So float 32 uses less memory because it's only 32 bits, like a regular integer. But because of this, it can approximate less of the real number line. So there are numbers, there are a lot of numbers, there are infinitely many numbers of the real line that this type cannot fit. You cannot represent certain numbers with float 32, that's it. However, if you use more bits, if you use float 64, which uses twice as many bits, you can represent many more types of real numbers. So there's a trade-off. You can use float 32 to use less memory, but it will be less accurate. Or you can use float 64, which uses twice as much memory, but is many times more accurate. So this has long been known. Your computer uses this, your phone uses this, everyone uses this. For large language models, you can do the same. You could theoretically train your language model using float 64, but this will literally double the amount of computation, the amount of memory you will need. So usually training is done using float 32, which is 2 times smaller. But you can also use float 16, which is which uses 2 times less memory again, and so on and so forth. So the idea here is that you train in, for example, float 32, use 32 bits per number, and then you use sophisticated methods to convert each individual number into one of these on the slide. You can use other methods to represent floating point numbers. So the idea here is that you use less memory and thus less computing power, but you get numbers that are less precise, as shown on the slides. So this isn't specific to large language models at all. This is widely used in computing in general.
Yeah, but still impressive. At least
actually not like exactly like this. Nowadays, most models are trained in BF16.
Yep.
And transformers are trained mostly in FP8. There are lots of experiments to train other models in FP8, but these trainings are unstable. So for some reason, only transformers are great at training at FP8.
Yep. So the goal is to use less memory and less compute because we are always constrained by memory and compute, but to remain as precise as possible because these number formats aren't random. They are specifically designed to use less memory, but to be as precise as possible. So of course, if you want to train larger models, you naturally want to use less memory. If you want to train like ChatGPT, which has billions of parameters, you don't want to buy massive RAM. You want to store them in less RAM. So you use this kind of model, this kind of representation for floating point numbers, even for training. So you can use these fancy formats for training and for storage and for inference. So this is great. You can go to Hugging Face. This is like a massive storage for open source, well, open weight language models. You can go there and see what kind of models they provide. Many of them are quantized. So now you know what a quantized model means.
Great. It was, I would say, a bit tough session today, but eventually we learned a lot of important and I would say useful things about large language models. And now we understand at least at some quantization what they really do behind the scenes. And thank you very much, George. If you have any questions, guys, it's time to ask them, unless we have them. I think that we can go and have some rest. Okay. So in the meanwhile, we will send you new portions of assignments. So we will come up really soon. I think perhaps a couple of hours. So today for sure we will hand them out, and also we will provide you perhaps some links to helpful resources, or we will include them in the assignment. So it's still in progress. Okay, so stay tuned, guys, and thank you very much for your attention.